lecture on the heart. Final one, I swear to you, I swear to you. And we were just talking about things that affected heart rate a moment ago. Talked about regulating it earlier. Now we got to talk about things that affect stroke volume. There's an old adage in real estate that the three most important things in real estate are location, location, and location. In a similar vein, the three most important things that affect stroke volume are preload, preload, and preload. There are some other minor things, contractility, and afterload. So, we know what stroke volume is, the volume of blood ejected by one ventricle per beat per cardiac cycle. What we got to do is figure out, well, what exactly is this preload, the thing that affects stroke volume? What exactly are those other minor influences, contractility and afterload? That is our task at hand. So, preload, in a nutshell, refers to the degree of ventricular stretch, which, in other words, is your end diastolic volume, because the stretching of the ventricle will be due to the contained blood. Basically, as preload goes up, stroke volume goes up too. Eventually, it does level off and come back down because there could be overstretch of the heart muscle. But basically, the more stretched the ventricle is, that's preload, and the more stretched it is, the more blood's going to come out. All right? And the thing that stretches the ventricle is the EDV. All right, let's unpack this a bit. All right, let's suppose that you get up. I'm assuming you're sitting down right now. Let's suppose you get up and you start doing some squats. And as you do this, you're going to have blood return to your heart from your leg muscles, quads, glutes, gastrocs, all going to power blood back to your heart, more so than when you were sitting down. And when this increase in blood comes back to your heart, the ventricle is going to stretch. What that does is create a better overlap between actin and myosin, and therefore we get more ventricular tension, and thus stroke volume shall rise. Okay, there is another way to phrase this. These two guys, Frank and Starling. I think the handsomer one is Frank. The other guy is Starling. I'll let you figure out which one is which then. Basically, these dudes did an experiment on doggies where they would adjust the amount of venous return, the amount of blood going back into the heart, and see how that impacted stroke volume. And the really simple way to state the relationship between preload and stroke volume is whatever goes in, goes out. Whatever goes in gets pumped out. If more comes back, more gets ejected. If less comes back, less gets ejected. It sounds pretty straightforward, and it's actually really important. All right, moving onward. Contractility. This is how hard the ventricle is squeezing / contracting, irrespective of how much blood it is, how stretched it is. So pretty much think about it as squeezing force. And basically, you squeeze harder, more comes out. All right, harder you squeeze, more comes out. Primary things that affect contractility are two things. Well, the cardioacceleratory center, and thus norepinephrine, plus hormonally epinephrine. These two guys both cause contractility to go up. Now, I want you to think about why contractility has to increase alongside heart rate. Why does contractility have to increase alongside heart rate? Think about that for a while. Write that down. Think about it. All right, last thing that impacts stroke volume is the afterload. That's the pressure that's going to be required to push open the semilunar valve. In other words, the afterload is another way to talk about aortic blood pressure. Now, here's the deal. Suppose your pressure in the aorta was really high. Would that make it easy to open the valve here? No, of course not. And if it were not easy to open that valve, well then you would have to spend more energy opening the valve. You have less energy to spend pushing blood out. Thus, your stroke volume would go down and you'd have more blood left over. Your ESV would go up. Check this out. This is the left ventricle of a severely hypertensive patient. Okay? So the left ventricle is huge. It's huge because this person had to constantly work very hard to open that aortic semilunar valve in order to eject blood. And as a result, their left ventricular myocardium hypertrophied like crazy, got so big, which is actually not a good thing, as you can probably tell because we're looking at a transverse section of this person's heart. So this is not a good thing. Heart attack is much more likely to happen. Hard to feed this big muscular heart. All right, so if aortic pressure goes up, in other words, if afterload goes up, stroke volume goes down. By the way, can you see trabecular carinae in here? You totally can. All right, couple questions here for you to do at your leisure. I'll quiz you in class. Another question about a cute puppy. Oh, right here. And last but not least, exercise, endurance training. This guy over here is, I think that's Dave Scott, who was a absolute beast in triathlon a long time ago. And as such, he did a lot of endurance training. And in terms of the heart, basically endurance training has three great results. All right, the contractility of the left ventricle goes up like crazy. The heart is better at squeezing. It can squeeze harder. The size of the chamber, not the wall, but the chamber goes up too, allowing it to accommodate more blood, which allows it to pump more blood. And the coronary circulation gets more diverse. It elaborates. It gets better and bigger, which is good for feeding and maintaining any increase in the heart's activity. So, wonderful, fantastic news, ladies and gentlemen. We are done with the heart. And I will see you guys later.